Let's look at a couple more examples of these optimization word problems. All right, so a builder wishes to fence in 30,000 meters square of land in a rectangular shape. So 30,000 is my area right in here. The fence along the front part of the land is $50 a meter. On the other three sides, it's $10 a meter. Now, I don't know that the length and the width are the same distance, so I'm going to say the length is X. So each of these would be X, and I'm going to say the width is Y. Each of these would be Y. So like if this side over here was 10 meters long, then the cost would be 10 times 50, right? And so the cost of this side is going to be 50X. The cost of this side 10Y, here 10X, and here 10Y. And if I put all four of those together, then that's going to be my total cost. So that's what we've got right here. All right, we could simplify that a little bit. So obviously put our 50X and 10X together and put our 10Y and 10Y together. So here's my cost. Now the problem is you cannot solve for X and Y at the same time. So there's got to be other information in this problem that would allow me to get rid of X or Y. And so if I go back, it says the builder wishes to fence in 30,000 meters square. Meter square is a hint for me, right? Because a square unit is area. So what's getting enclosed here is the area. So that means the area of this figure is 30,000. Well, how do you find the area of a rectangle? It would just be length times width, right? So I could say X times Y is 30,000. And then I could either replace X or Y. It doesn't matter in this problem. I chose to replace Y. So I'm going to solve this equation for Y. So I'm going to divide both sides by X. And so I'll have Y as 30,000 over X. So let's take that and let's put that right here for this Y. And that way I'll only have one unknown. All right, so if I simplify that, I'm going to have 20 times 30,000, which is 600,000 over X. I'm going to write that as X to the negative 1 just because it's easier to take the derivative that way. All right, now why am I taking the derivative? Because we are trying to find the minimum. So the minimum can come from a relative extrema or from an endpoint. So let's start with finding our relative extrema. That means that we're going to find our critical numbers, right? We're going to take the derivative, set it equal to 0, and find our critical numbers, all right? So if I take the derivative of 60x, that's 60, and then negative 1 times 600,000 is negative 600,000, and then subtract 1 here, and that's going to be x to the negative 2. So you also could write it like this, where you move your x to the negative 2 down to the denominator and make it x to the positive 2. And to solve this, it'd probably be easier if I put one of each of these on each side so that I could get x by itself and solve for it. All right, so let's think about critical numbers. So critical numbers are going to be where our derivative equals 0 and where our derivative doesn't exist. Now, this is my derivative, or written this way, same thing, right? So my derivative doesn't exist where I have a domain issue, where I have a fraction or a radical. So for this one, I have a fraction. And remember that when you have a fraction, you're going to say your denominator cannot equal 0. So that would mean that x cannot equal 0. Okay, well, is that even a possibility for this problem? If you go back up here and say, okay, if x is 0, then that means my area, 0 times anything would be 0. That means my area would be 0. And it can't be because they told me that my area was 30,000. So we're going to toss 0 because that's not a possibility. So I don't have to worry about that critical number because it's not relevant to this problem. All right, then let's go ahead and solve, and let's find our other critical numbers. And again, that's just by setting the derivative equal to 0 and solving. So here I can cross multiply. So I'd have 60x squared equals 600,000. Then to get x squared by itself, divide both sides by 60. And then I'm going to take the square root of both sides. So that would give me plus or minus 100. All right, so again, what does x represent? X represents the length of this side of the fence, right? You can't have a negative 100. So that means that the only critical number that I got was positive 100. Now, I'm going to test that just to make sure that that's actually a minimum, not a maximum. So I'm going to make a sign graph for the first derivative, and I'm going to pick a test point. So I just picked 1. I couldn't pick 0, right? Because it doesn't exist in this problem. So I'm going to pick 1, and I'm going to plug it into the derivative. All right, so here's my derivative right here. So if I take 1 and I plug it into that derivative, I'm going to get 60 minus 600,000. So that's definitely going to be a negative value. So it's negative at 1, and then cross a single root, the sign changes. So anywhere my first derivative changes from negative to positive, that is going to be a relative minimum. And since that's my only minimum, then that is going to be my absolute minimum. Now, remember that you always have to check your endpoints. So if I'm thinking about endpoints on this, I'm saying, okay, what's the smallest value? Because we're talking about values for x, right? That's what we have in our equation. What's the smallest value x could be? Well, the smallest would be 0, but we've already said that's not a possibility. So I could go right up to 0. X could be 0.00001. That'd be preposterous because that means y, would be significantly larger and there wouldn't be much area, in terms of width. But that is a possibility. But I don't have an endpoint. If I'm going right up to 0, but I can't include 0, that's a parenthesis. That's not an endpoint. So I don't have any endpoints to consider. So my relative minimum is my only minimum. So it is going to be my absolute minimum for my absolute minimum cost. Okay, so go back and notice that it says find the minimum cost of that fence. Okay, well, this was my cost equation. So I need x and y for that. I already know x is 100, and right up here we said y was 30,000 divided by x. So that would just be 30,000 divided by x, 30,000 divided by 100. That would give me 300. So now I know x is a positive 100, y is a positive 300. Now I can plug them into this equation. So I could say 60 times 100 plus 20 times 300, and that's going to give me the minimum cost of the fence, which is what we did right here. All right, let's talk about the setup of this next problem that is an actual problem from my lab. All right, so it says set up and evaluate the optimization problem. It says you're constructing a cardboard box from a piece of cardboard with dimensions 2 by 4. Okay, so you can see this is 2 meters and this is 4 meters. It says you're going to cut equal size squares from each corner. Okay, so I don't know what the size of these are. I just know that they're the same. So like, let's say that this was a quarter of a meter, then that means this is a quarter of a meter and this is a quarter and this is a... So we could go through and literally, like if you took a piece of paper and you tore out this corner and you tore out this one and you tore out this one and you tore out this one, the reason they're doing that is it says you want to fold the edges. So once those are gone, you can fold this side up and fold this side up and this side and this side. And that's how you get your open topped box, your box that doesn't have a lid on it. Okay, so if we do that, if this was 2 meters long and I took this X off and I took this X off, remember we like tore off this piece of paper, tore off this piece of paper. So that would leave me with 2 minus 2x for this length. All right, same thing here. If this total length was 4 and I took off this x and I took off this x, then that would be 4 minus 2x. So volume is going to be length times width times height. So volume is always area of the base times your height. So the base of this is a rectangle. So area of a rectangle, of course, is length times width and then times height. So we figured out that our length was 4 minus 2x and our width was 2 minus 2x. And now we just need to find our height. Well, if you take these sides and you fold them up, this is going to be the height of your side, right? And that's x. So we could say that length is 4 minus 2x, width is 2 minus 2x, and height is x. So we're trying to maximize our volume. So this is the formula we're going to take the derivative of. I would go through and FOIL this out first and then distribute this instead of having to do like a product rule or something. So if I multiply this whole thing out, then I can just use power rule. And then I'm going to take that polynomial that I get. I'm going to, after I've taken the derivative, set it equal to 0 to find my critical numbers. And then find my relative maximums, and then see with those or the endpoints which one would be the highest value to be my absolute maximum, my largest value. When you go to put your answers in, notice that, for your sides, let's say that we figured out that this was 1.5 over here and this was 3.5 over here. Make sure that you put those in the shorter and the longer sides. All right, one last thing that I want to mention to you is there's a problem dealing with revenue, cost, and profit. So profit is just how much you make minus how much it costs you to make it. So, like if you are selling t-shirts for $20 each, you still have to buy the t-shirt from the store for $5. So you might sell them for $25 each, but you got to take off that $5 you paid for it, so your profit would be $20 each, right? So we'll need that for that problem that we're working on.